afternoon. So I'll be basically describing Qedma and the solutions that we've been building for the last 2 years. So first, who we are. I think at Qedma we're really blessed to have a really world-class team. I want to also highlight my co-founders, Asif Sinai, the CEO, Professor Dorit Aharonov was one of the first to prove the fault-tolerant theorem for quantum computing. And we have 34 people, out of them 15 PhDs and 6 faculty members. Okay, so let me describe also the position of Qedma in the quantum computing stack. So if you view kind of broad stroke the quantum computing stack, at the bottom level you have the physics, the processor, the pulse level. At the top you have the design of quantum algorithms and applications. And in the middle, what we are basically developing at Qedma is all of the layers that bridge the physical level with the algorithmic level, including characterization, gate optimization on the pulse level, compilation meant to reduce and suppress errors, and later on, development of a quantum development environment. So if we want to get into more details of what we're addressing at Qedma, so let's ask, what does it take to actually build a useful quantum computer? So as we all know, there's 2 major axes in this respect. One of them is increasing the number of qubits. And I think we've been seeing kind of steady progress, and most hardware providers also have a clear roadmap, at least at the intermediate timescale of how to proceed. The other axis is, of course, reducing the gate errors. And these are not orthogonal axes. In fact, I think if you view the errors in the gates for the largest system available, I think we're seeing progress which could be significantly accelerated, and that's what we're addressing at Qedma, basically accelerating the progress in reducing gate errors. So if we want to be more specific, we're developing several solutions. The first solution that we've developed is a solution for flexible characterization of multi-qubit devices. I'll describe the solution with more detail, but in broad strokes, it provides very detailed description of the errors occurring when you apply logical gates, and it does so with cutting-edge speed-to-accuracy trade-off. And then when we have the results of this characterization, we can fit it in to basically 2 modules that are meant to reduce the errors. One of them is an automatic gate optimization module, which basically suppresses errors at the hardware level. And the other one is basically a compilation module that does error mitigation and correction and reduces errors on the algorithmic level. So let me now describe our flexible characterization solution. So as I said, this is a very detailed characterization of multi-qubit devices. It's very sensitive to many types of errors, like coherent errors and crosstalk errors that are very hard to extract using conventional methods like randomized benchmarking. For example, in this plot, we could see a description of a whole device with the level of errors on single-qubit gates and 2-qubit gates. We could zoom in on a particular gate, say the gate between these qubits 5 and 6, and we could view individual errors of this gate, including its effects on the neighbors of these pair of qubits. In particular, for example, we could choose to look at the errors occurring between qubits 2 and 6. These are crosstalk errors or residual interactions between these qubits occurring when you actually apply this C0 gate. And I'll go into more details in a second. So in order to kind of describe more detail what we're giving, let's actually discuss how we're basically parameterizing those errors. So we're describing the gates as process maps, and we're parameterizing them as an exponential of Lindbladian, which is a time independent. Of course, the physics is strongly time dependent, but this is just a parameterization. That the Lindbladian has basically 3 parts. It has the ideal gate generator, H0. It has the coherent error part, which is the basically error Hamiltonian, and it also has the dissipation part, which is basically describing the dissipative or irreversible errors. And as an example, you can see here we can have errors on the active qubits, either single qubit errors or 2-qubit errors. and also crosstalks, which are basically residual interactions between the active qubits and their surroundings and their surrounding qubits. And I want to emphasize that the parameterization we're using is actually very flexible. It's user-defined. So the user can actually define an error model that he thinks describe properly the physics of his device, and we can help him basically understand which parameters are important and which parameters are not, in order to zoom in on the correct physical description of the errors in the device. I also want to emphasize several unique features of our characterization. We can characterize non-Clifford gates, for example, fractional 2-qubit gates. We have an extensive set of tools for model verification. We could characterize full computational layers, and I'll show you some examples. And we can also characterize non-Markovian errors such as leakage and history-dependent errors. For example, this is an experiment in which we've detected a flux tail, which carries kind of memory effects in the system, and our ability to basically extract it was, helped us actually explain, predict kind of experimental data for other experiments. Just in terms of timescales, how fast our characterization protocol runs. So if we want to, for example, just characterize just a single 2-qubit gate, including the crosstalk with the neighbors, we'll do this with around 10 to the 5 shots. For a superconducting device, this would take around 1 minute. And if we want to characterize a full layer, meaning a situation where we apply gates in simultaneously, we'll do this also with the same amount of time, irrespective of the size of the layers, how many qubits actually participate in that layer. With these times, we're able to basically give you 90% statistical accuracy, meaning the next significant digit of each error parameter. And importantly, our post-processing, classical post-processing time is real time, which means that you can feed in directly the results of this characterization to other modules, such as modules responsible for reducing errors. Okay, so now I want to basically give you a few examples. So the first one would be an application of our full device, a module we call full device characterization, which basically sweeps through the whole system, characterizes all the gates, and I'll also show you the predictive power of the parameters we're extracting. Okay, so here's we ran this basically module on a system called IBM Guadalupe. This system has 16 qubits. In this kind of sweep, we've characterized 32 gates. It's around 2,000 parameters. We've used around 1 million shots. And the wall time for this was around 90 minutes, although most of this wall time occurs due to basically controller delays, which could be fixed. And we believe they will be fixed in the very near future, reducing this time to around 20 minutes. So this is an example of parameters, error parameters for a single qubit gate. This is, say, qubit number 12. It's a single qubit gate acting on this. We're basically extracting the errors on this qubit and its neighbors. You can see that there's a large error, Z error on the active qubit. These are the magnitude of the error. It could be either positive or negative, so it's in a coherent error. And we also have quite significant crosstalk parameters for this single qubit gate in this system. Another example is this 2-qubit gate. So you see this is the 2-qubit gate between qubits 5 and 8. Again, there are significant coherent errors on the active qubits, either single qubit errors or 2-qubit errors. There's also quite significant crosstalk errors, and I want to focus specifically on this crosstalk error between qubit 8 and 11. This is a residual interaction occurring when this gate is being applied. And what I want to show you here is that the parameters, this crosstalk parameter that we're extracting actually has predictive value. So what we're doing here, we're taking the model we extracted, and we're basically using it to predict the results of very simple experiments in which we're basically applying the CNOT gate n times. So on these plots, you see this n is the number of times we've applied the CNOT, and this is an expectation value of some observable. And you can see in the blue plot, you can see the prediction of our model. In the purple plot, you see a model which we trained without this crosstalk parameter. So we basically set this crosstalk parameter to 0 by hand. And you see that if we do this, this completely spoils the prediction of the model, meaning that the value we extracted with parameter is actually meaningful to explain predictions or to explain actual experiments, very simple experiments run on this device. Okay, so I know, my team complains that I'm very keen on looking at plots, and I guess you're also tired of seeing all of these plots by now, so I prepared another slide. And basically, you can see that we can verify all of these parameters. We have hundreds of these verification plots. This is how we make sure that what we're doing is actually meaningful. Here I've plotted like a histogram of all of the coherent errors in this device. The yellow are the active qubit errors. You see this device have actually significant coherent errors. And on the blue, you see the crosstalk errors. And you see that this device also, the tail of this distribution actually also has significant crosstalk errors. So you need to take them into account if you really want to do things correctly. Okay, so I want to move on. I want to describe our layer characterization protocol. And specifically, I want to also show you our ability to characterize non-Clifford gates. So we're looking now at a layer where I'm applying two non-Clifford gates in parallel. These are fractional RZZ gates with an angle of pi/6. And this is some particular layer on IBM called kata. You can see the coherent errors of these layers, the largest coherent errors. There are significant active qubit errors here, but also significant crosstalk errors. And in fact, we've characterized many layers of this type, and you can see that the crosstalk errors in layers is actually much more significant than the crosstalk errors in isolated gates. For example, there are many crosstalk parameters that are beyond 1% for layers, where this is not the case for isolated gates. Okay, so now I've showed you our layer characterization. I want to move on to the automatic gate optimizer, basically using the results of our characterization to optimize quantum gates and increase their fidelity. So let's return to the layer I've just described. And again, the yellow bars here are the errors of the kind of raw gate. This is just a rescaled C0 to give us the correct angle of pi/6. And you can see that using the characterization parameters and by adding correction pulses, single qubit correction pulses, we've been able to basically almost completely eliminate all of the errors on the active qubits, significantly increasing the fidelity, basically almost eliminating the coherent contribution to the infidelity. You can see also that we were not able to correct the crosstalk errors with single qubit correction pulses on the gate level. We have other methods, which I'll not describe here, to also take care of these crosstalk errors. Now, what I want to emphasize that if you have crosstalks in your device and you want to do this type of error suppression, it's actually important to correctly characterize the crosstalk. Because if you don't do that, you're going to have systematic errors on the rest of the parameters you're extracting. And for example, if we do this set of correction pulses and error suppression based on a characterization which is not sensitive to crosstalk, we indeed suffer from these systematic errors. In the purple bars, you can see what happens when we try to do error suppression without, based on a characterization that's not sensitive to crosstalk, and you see that this performs significantly worse. You can also look to see what would be the result in a kind of a simple experiment when you run a circuit when you apply this layer n times. N again is the number of times we apply this layer. And you can see that the yellow is the performance. This is a deviation from the ideal value of some observable. You can see that the observable deviates strongly from its ideal value for the bare gate. And the performance is significantly improved by doing our error suppression. This is the blue plot. And if you do this error suppression with a crosstalk insensitive characterization, you get significantly worse results. This is the purple plot. Finally, I want to also show you that there are very simple experiments where this error suppression is visible. So this is just a simple Ramsey experiment in which you do a very simple circuit. And you see that if you compare the yellow circuit, the yellow plot to the blue one, you see that our error suppression significantly improves the performance of this layer, and you can also see this in the improvement in the fidelity. So finally, I want to emphasize I've described several solutions. I've described our ability to fully characterize errors in multi-qubit systems. I've described our ability to use this characterization to automatically suppress coherent errors with our cutting-edge runtime. I did not describe our ability to basically recompile circuits and suppress errors on the algorithmic level using this characterization, and we'll be happy to discuss this offline. And I want to thank IBM for allowing us to share this data and for their support. If you're a hardware company interested in testing our solutions, we'll be happy to discuss. And thank you for listening.
Thank you, Netanel. We do have 4 minutes left for questions. So let me do the one up front first, and then.
To what extent is your technology applicable to or generalizable across all quantum computers versus just restricted to IBM? I know that's where you've tested, but how generalizable is it?
No, yeah. So I should have stressed that. We've tested this technology across many types of systems. And I don't want to say it's hardware agnostic. I think that's foul, but with very kind of minor level of adaptations, it's transferable to any type of quantum computing platforms.
And we have another question from the back here.
Thanks a lot for the very nice talk. I have actually 2 questions. The first one is, what kind of error mitigation techniques are you using? And the second one is, have you benchmarked it against what IBM is already doing for error mitigation? So I know that they have a module for error mitigation. So have you?
Yes, thank you. Yeah, so I did not get into details about our error mitigation technique. I don't also maybe get into the question of what exactly type of error mitigation we're using. I could tell you that for the sizes of circuits that are manageable today with error mitigation, we can give basically an increase in the overhead by several orders of magnitude. So if you compare runtime of our error mitigation, of an error mitigated circuit to the best known published error mitigation method out there, our error mitigation method will give you a runtime which is several orders of magnitude faster, achieving the same accuracy.